guys, I had to make another video because I want to just publish some things when they're on my mind long enough, and I just want to get rid of them. Like, the reason why I made a calculator programming series in the first place wasn't so much that I wanted to just like grow something new. It was like I had this idea and it was just old, and it was like I showed too many people, hundreds of people, kind of throughout my life for a few years, like, look, I'm programming a calculator, you can do this and you can do that. And it was like, I don't want to do that for my whole life. So I was like, oh, I can document this, I can put it online, I can archive it, and it's there online forever. And turned out to be, episode 1 of this big thing that people like to watch. So, and some people said it was the best one online, and I was just like, well, I was just posting something that I had done for like 10 years. So, but I was just happy and relieved when I first made my first episode, because I was like, oh, I don't have to show people how I like to make these calculator programs anymore. It's like online archived, it's history, and people can just watch that. I don't have to worry about it. I don't have to be alive, it's just there. Babies. No scratching. So, physics. When I was in the Army, people would argue with me about, I told them, if you dropped two objects, like two, let's say, large steel balls that were solid steel all the way through, the same density, I told them the larger one is going to fall faster if there's air friction. And they didn't seem to understand the difference between air friction and not air friction. They're like, oh, you're dumb, yeah, they fall the same speed. They don't fall the same speed if there's air friction. Because, and this is one of my arguments that I brought up, if you slice a cube into 8 smaller cubes, there's more surface area but the same amount of volume. Well, you can't group together and drop 8 cubes and compare that to 1 cube. Actually, you can. And by slicing it up, you make it the same size as the small cube. So dropping them together as a set, but separately, means they'll fall exactly the same as the 1 cube, because you're dropping them separately. So, yeah. A large cube has the same volume, the same mass as the sliced multiple cubes, but it has less surface area. That's the point. Surface area changes, if you want to call it a tuple, that includes the shape and total surface area, or redefine, another, it depends what your definition of shape is, but if your shape defines how big the thing is, then basically shape matters for how fast something's going to fall, because size also matters. They're not scaling the problem correctly. They think if you drop a ball, it doesn't matter how big it is. It matters how big it is, because you'd also have to adjust your definitions of space and time themselves. And here's where I get confused on a few things. Like, why do people not understand this? Like, I got in an argument with my friend about how Neil deGrasse Tyson would always talk about how spaghettification would cause somebody pain because they'd be stretched. It's like, but space-time itself is being stretched, and therefore, by definition, you're not being stretched in the traditional sense, because being stretched means that within the space and time that you're in, I take up 5 inches, somebody stretches me on a torture device, I take up 6 inches, right? If somebody stretches space-time and I take up 5 inches in the space-time, it doesn't matter how much they stretch the space-time, I still take up exactly 5 inches in that space-time, right? They're stretching me relative to some constant, or relative to another observer who, is not, who has to be out of line of, there has to be some mass where it's stretching in a non-uniform way, where for somebody far away, if I'm next to a celestial body, that's, when you draw a triangle through that, it's going to be different. But when you're just talking about, I'm here and I'm on a planet, or I'm next to a black hole, and it's just uniformly stretching me, space-time itself, that just becomes a force from my point of view. And because I'm accelerating, I don't even feel that force. So you wouldn't feel a black hole unless, unless it's actually somehow stretching you in a way that your body can detect it. So I'm just going to put that out there. You have to at least be able to detect that something is stretching you to even make the argument that you'd be feeling pain or that you would be being destroyed or compressed or something like that. Because if you can't even detect it, then then it's just an observer from outside, from away from the black hole, observing you closer to the black hole, and you're just talking about that. But the funny thing is, and obviously I'm not a physicist, but what I don't understand is why are people always talking about like how they need to find quantum gravity or they need to find some representation that explains, like they're trying to find a graviton or gravity particle or something like that, and it just doesn't make sense to me because from what I understand of general relativity, it's a more generalized, literally more generalized model that's more generalized than one that assumes that space-time has to be constant. It's like the speed of light was found to be constant, but that's relative to what we already consider constant, like time, because we can't assume that the speed of light is literally constant at all levels of abstraction. It's like saying like, oh, I walked a couple miles and I realized that was um, my house wasn't flat. I walked far away from my house and I saw that my house was actually curved a little bit. It wasn't flat. And so therefore my house is curved, but the ground is flat. Well, hold on a second. What do you mean the ground is flat? The ground is flat relative to your house, but if you zoom out more, you're on a planet, it's curved. So it's like it's light is flat compared relative to time, light is flat, but relative to other constants, it could definitely be changing. It's not literally, the speed of light is not literally constant in all contexts. It's assumed to be constant in the context that was trying to define why why we're measuring it at the same speed all the time, and it defined space and time to be very relative to compared to it. So what I don't understand is where do we get the concept or the idea that somehow we need to re-explain gravity when it's already fundamentally explained? Like there's nothing in physics that indicates, oh, we live in a Minecraft, flat Euclidean universe, which we're just going to pretend is stretched, but we're not going to actually believe it. Even though that's what the math and the physics says, is that it's fundamentally stretched, we're just going to assume that, somehow that's just magic and we're not going to actually believe it. And we're going to try to explain this using quantum physics. It's like, no. The whole point of general relativity and special relativity is that classical time and classical space are stretched, and that light is the constant when trying to determine these astronomical distances. Light speed is what I mean by is a constant. Light speed is a constant in that context. Now, if you zoom out more in terms of scale of time and space, maybe that also isn't as constant. But the point is that time is something that Newton was thinking, you could have a master clock and it's always the same for everybody no matter where you're going. And that just turns out to be false. Same with space measurements, And the result of that knowledge is that gravity is a thing because it turns out that if you have mass, the time and space is stretched such that any object is going to just exist as moving towards that. So What I don't understand is why somebody thinks they would need to come up with like a quantum or standard model explanation. Doesn't make sense to me. Because it wouldn't make sense as a particle. Because particles exist within space-time, and they have events that define our tracing of them. So somebody explain to me why what exactly the what exactly is expected in a unification theory, because I don't think it doesn't make sense to me that quantum physics needs to add anything to explain gravity, basically. Like, maybe there's something to do with explaining mass converting, but just as a fundamental explanation of gravity, that's not a fundamental force. It's a fundamental result of the structure that you already get from the space-time structure, as far as I understand. Like I said, I'm not a physicist. I'm not really. I don't work with the math, but I look at the model, kind of look at examples. I look at models and try to understand the concepts, and that's where I'm kind of like, what's actually going on here in the community? Because to me, it's not adding up. Because if they understand what I think they understand, they wouldn't be looking for that as the solution. It wouldn't actually make sense. Or maybe that would be a good question for Penrose to answer. If he'd be willing to actually watch one of my videos, that would be cool. I don't think I'd be at his level, but maybe he would have a good answer for why he thinks some people are trying to look into that. So let me know what you guys think. As maybe if you're a physicist, or maybe if you just understand models kind of well. Like I would say maybe I'm just good at modeling things. I'm not even much of a professional mathematician, but I appreciate math. If I have to put put an adjective on myself, I'm an appreciator of math, I suppose. Let me know. Thanks.